Assalamu alaikum warahmatullah. Hello guys. Today we will talk about chapter 12, applications of deep learning. Let's get started. So, applications of deep learning. So we talk about algorithms and some kind of architectures like CNN, RNN in previous videos, and we talk about regularization, about gradient descent, about very simple and earliest these neural network architectures. And today we will talk some applications we see every day on our life, and applications which are applied as a commercial product to some service as services. And one thing I want to mention is that while one goal of deep learning is to design algorithms that are capable of solving a broad variety of tasks, so far some degree of specialization is needed. For example, vision tasks require processing a large number of input features, pixels for example, per example. Language models requires modeling a large number of possible values, words in a vocabulary per input features. For each task, there are different methods, different approaches to train to get the task done. So deep learning is based on philosophy of connectionism, right? So while one individual neuron or individual feature in machine learning model is not intelligent, cannot do tasks, cannot do even very simple tasks. However, a large population of this kind of single neurons acting together can exhibit intelligent behavior. So we can see, for example, if we build very small neural network, we cannot solve even XOR problem. But if we build larger, if we increase the number of neurons and add some activation functions, we can solve problems, and we can solve even big problems also. So, because of the size of neural network is critical, deep learning requires high performance hardware and software infrastructure. Traditionally, neural networks were trained using the CPU of a single machine. Today, this approach is generally considered as insufficient. Because of difficulty of writing high-performance GPU code, researchers should structure their workflow to avoid needing to rewrite new GPU codes to test new models or algorithms. This is typically done in frameworks like PyTorch and TensorFlow. Here you can see three different papers. The first in the left talks about how to use CPU efficiently, a combination of CPUs to train large-scale deep learning models. Second paper in the middle talks about how GPU can boost your training process. The second paper actually it was published in 2005. And the last paper talks about high performance in convolutional neural networks for document processing. So here I want to say that building large-scale deep learning models require good or even strong hardware infrastructure. And in many cases, the computational resources available on a single machine is insufficient. We therefore want to distribute the workload of training and inference across many machines. Distributing inference is simple because each input example we want to process can be run by separate machine. This is known as data parallelism. However, model parallelism is multiple machines working together on a single data point with each machine running different part of the model. So in PyTorch or in TensorFlow, we can easily call these APIs and do this processing, parallel processing, if we have multiple GPUs, and we call it as model parallelism. Data parallelism during the training is hard. Traditionally, gradient descent is sequential algorithm. The gradient at step t is a function of the parameter produced by step t minus 1. This can be solved using asynchronous stochastic gradient descent. This is another algorithm. In this approach, several processor cores share the memory representing the parameter. Each core reads parameter without a lock, then computes the gradient and increments the parameters without a lock. So this is asynchronous workflow. They work together as a friends, different processors to compute this gradient, and they share with each other. It is, I think, complicated, and we shouldn't talk about this today because, yeah. So it is about parallel processing. Let's talk about model compression. In many commercial applications, it is much more important than the time and the memory cost of running inference in machine learning model be slow than the time and memory cost of the training be slow. So it is important how expensive to run the model in inference for commercial applications, rather than how intensively required to train these models in training process. For example, if we have a model which do face recognition, if we are waiting, if this model cannot be run on edge devices, if this model is very huge or it has a lot of memory and different kind of parameters, then we cannot run on edge devices. It means we cannot use it as commercial application. So it's very important how fast and how memory efficiently runs a model, and we always try to find this trade-off between accuracy, between the performance, and between this time and memory cost. A key strategy for reducing the cost of inference is model compression. So basic idea of model compression is to replace the original expensive model with a smaller model that require less memory and runtime to store and evaluate. For example, we apply this kind of compression algorithm and it becomes small model. So now let's talk about computer vision. Computer vision is one of the field, and it is traditionally been one of the most active research area of deep learning application, because vision tasks is generally very straightforward for human animals to do, but it is challenging for machines. So most deep learning research on computer vision has focused not on such exotic applications that expand the realm of what is possible with imaginary, but they are focused on how to replicate the human ability, like recognize humans or recognize objects or object detection, etc. So in computer vision, if you remember, we talked about CNN, how CNN can benefit in computer vision, and one of the important thing is that to have good model, this kind of applications require sophisticated preprocessing because the original input comes in a form that's difficult for many deep learning architectures to represent. So preprocessing is the task that allows to model to learn more easier the input data. For example, we can do normalization, reducing the range of the pixels, or changing the size of the image, or doing some data augmentation, or for example, subtracting the mean across the training examples in each pixels, and etc. And sometimes preprocessing may also damage. Here's a little bit complex things. So it's about computer vision, basically. So let's talk about speech recognition. Speech recognition is also another active field of research in deep learning. So what is speech recognition? It is task to map an acoustic signal containing a spoken natural language utterance into the corresponding sequence of words intended by a speaker. Speech recognition also benefits from deep learning, of course. Initially, deep learning was used as a supplementary tool for speech recognition. However, later on, it became important key at speech recognition. That's what I know about speech recognition. So basically, we take these utterance, these signals, and we give to the model, and model predicts the sequence of text from that signals. And let's talk about another very active field of deep learning is natural language processing. So NLP is a use of human language like English, Korean, French, and etc. by a computer. NLP includes machine translation, summarization, and etc. A language model is defined as probability distribution over sequence of tokens in natural language. The earliest successful language models were based on the models of fixed length sequences of tokens called n-grams, and n-grams is a sequence of n tokens. Training n-grams models is straightforward because the maximum likelihood estimate can be computed simply by counting how many times each possible n-gram occurs in training set. However, this kind of n-grams suffer from curse of dimensionality, which means that as we give a lot of data, the dimensionality increases and the dimensionality becomes sparse, because actually if we give a lot of data to these n-grams, their dimensionality increases, but actually in inference not all these different combinations, different words will be called. So in order to overcome this curse of dimensionality, neural language models were presented as a solution to overcome this curse of dimensionality problem for modeling these natural language sequences by using distributed representation of words. So it's another big topic. Let's talk about neural machine translation. So machine translation is a task of reading sentence in one natural language, like English or Korean, and emitting a sentence which is equivalent meaning in another language. For example, translating from Korean to English. As an input text, we give some Korean word, and we have this typical structure pipeline of the machine translation. So we give some text, for example, in Korean, and we give it to translator. Translator receives this text, and it gives different variations of the equivalent meaning in English, and the evaluator selects the best translation. That's how machine translation works generally. So we talk about speech recognition, we talk about computer vision, we talk about natural language processing. Let's talk about other applications. There are different applications in deep learning. You can create your own application. So another application is recommendation systems. So for example, we use Amazon, Instagram, Netflix, and etc. We have a lot of data. We need recommendation systems. So there are two common algorithms, recommendation systems. One is collaborative filtering. Second one is content-based recommendation systems. They are also benefiting from deep learning. So when making recommendation to users, an issue arises that goes beyond ordinary supervised learning into the realm of reinforced learning. Reinforcement learning requires choosing a trade-off between exploration and exploitation. So recommendation systems, we can build recommendation systems that can be complex, or that can be between this reinforcement learning and supervised learning. RL means reinforced learning, SL means supervised learning. So what is exploration and exploitation? Exploration is taking actions specifically to obtain more training data. Exploitation refers to taking actions that come from the current base version of learned policy actions that we know will achieve a high reward. Supervised learning has no trade-off between exploitation and exploration, because supervised signal always specifies which output is correct for each input. Another difficulty arises in context of reinforced learning besides the exploitation and exploration trade-off is the difficulty of evaluation and comparing different policies. So, to sum up, these recommendation systems are also another huge topic to talk, and it is also an active field of research, because day by day we are generating a lot of data and a lot of different informations, and building these good, sufficient recommendation systems require some advanced algorithms, some advanced techniques. So let's talk about another application. So according to the book, they are giving us another research direction, and another research direction is determining how distributed representations can be trained to capture the relations between two entities. These relations allow us to formalize facts about objects and how objects interact with each other. It is also another field of applications. So, to sum up, this is about chapter 12. So, this is about chapter 12, and congratulations, we have finished the part 2 of the book, which describes the modern practices involved in deep networks, comprising all the most successful methods. So if you watched our previous videos and this current video, congratulations, you did a very good job. And here, this is a summary of what I understood, what I read from the chapter 12. And in chapter 12, basically we talk about how deep learning is applied to these fields, and how they are benefiting from them, and that's all. So, thank you very much for your time. So we have finished successfully the chapter 12, and it means that we finished part 2 in our book, which has overall 3 parts. 3 parts, yeah. So that's all about today. Thank you very much, guys. If you have questions, write in comments. Bye-bye.